All right, so in this video we're going to talk about the attraction between molecules. So we've talked about the attraction of atoms to each other, or ions to each other in an ionic bond, but we're going to talk about how molecules will interact with each other. So a lot of the principles in chemistry really come down to the forces of attraction that two objects or two substances have for each other, or repulsions. Okay, so we have intramolecular forces and inter. So intramolecular forces are going to be within the molecule. This is going to be the force that holds atoms or ions together in the molecule or the formula unit. These are the bonds, okay? Intramolecular forces are very strong when you compare the attraction that molecules can have for each other. So inter, with an E, intermolecular forces are going to be the force of attraction between molecules, which is going to be much weaker. So it takes a lot more energy to pull atoms apart that are within a molecule or ions apart within the ionic compounds. All right, so an IMF is the attractive force between molecules. So once you have your attraction between the atoms, well, if you have, remember, if you have molecules and they're polar, they're going to have that negative and positive region, and then those things can attract that in the other molecules. Okay, so IMFs, or intermolecular forces, are going to be much weaker, and then sometimes these are also referred to as van der Waals forces, with one exception, which I'll talk about when we get there. Okay, so LDF, or London dispersion forces, happens between all molecules. All molecules are capable of what we call London dispersion forces. So the electrons within a molecule can move. Okay, so sometimes they move around and then they move into one particular spot, which creates a dipole. So you have them moved all in one spot. That creates that partial negative region and a partial positive region. The thing about this is because the electrons are not really fixed, you create the dipole and then it goes away. You create the dipole and then it goes away. So this is the weakest type of intermolecular force, but all intermolecular forces are dependent on a negative region attracting a positive region. So even with the London dispersion forces, it's about attracting the negative and positive region of other molecules. It's just these are temporary dipoles that are created, and that's the weakest type of intermolecular force because of that. Now, what you will see is that if you have a higher mass or if you have a higher surface area, that increases your London dispersion forces. But really and truly, that's not the reason you see this, okay? The reason you see this is because it's got more electrons that are able to create these temporary dipoles. So we call that more polarizable electrons. So if you have two molecules and you're comparing them, so let's say that I have CH4, okay, CH4, and then I'm comparing it to C2H6, okay? So when I'm looking at these two molecules, well, they're both hydrocarbons, so they're both made of just carbon and hydrogen, which means that I'm going to see a nonpolar molecule for both of these. Well, this one is larger, so it has more electrons, so it is going to be a stronger force of attraction versus this. So when we talk about this force of attraction, and I'm just like saying one molecule, so this one right here, if this attracts another one of those, okay, that's an intermolecular force. And with London dispersion forces, what that means is the electrons move in one spot of the molecule, and then that creates that negative and positive region, and then it attracts. So the negative region attracts the positive region of the other one. It's just temporary because those electrons are moving. So I have a picture of that. All right, so with this right here, what ends up happening, you have nonpolar molecules, okay, so there is no negative region or positive region right now. So what ends up happening is the electrons will sometimes move, okay, and now they're moving in one side, so that creates that negative region and a positive region. Well, and then if that happens with another molecule, well, that positive region right here can attract that negative region here, and once that attraction is made, though, they disappear. Those dipoles will disappear. Okay, so dipole-dipole happens when you have polar molecules. So these are permanent dipoles. The permanent dipoles attract each other, and it's going to be stronger than LDF because it's a permanent dipole and not a temporary one. So right here, okay, remember in a polar molecule you've got a partial positive and a partial negative region. So what ends up happening is now the partial positive is attracted to the partial negative of another molecule, so they stick together. All right, so hydrogen bonding is a special type of dipole-dipole. It's very, very strong. So this happens when you have a covalently bonded hydrogen it's covalently bonding directly to an O, N, or F, okay? So the O, N, and F, those are the most electronegative atoms that we have. And then you've got something with a very small nucleus, so you've only got one proton. So because of that bond right there, that creates a lot of polarity. Those electronegative atoms are able to pull the electrons much more strongly than the hydrogen can. Okay, so it's one of the strongest IMFs that we have. There is something stronger though. So hydrogen bonding happens when you have like a water molecule attracting another water molecule. So we know there was polar, and then your oxygen is going to be partially negative, and then your hydrogens are going to be partially positive, so they're going to be stuck together. So when you see these diagrams, I want you to understand something. So you see that right here we've got these dots, or you've got these dashes. Okay, those are going to represent intermolecular forces. That's the force of attraction between the molecules. If you see that you got a direct line, so right here, this nitrogen is bonding to this hydrogen right here with a line like this, that represents a covalent bond, okay? In order for something to be considered a hydrogen bond, the hydrogen that is covalently bonding, okay, within the hydrogen bond has to be directly covalently linked to a nitrogen, oxygen, or fluorine, okay? So right here we've got this dashed line. All right, that dashed line represents the intermolecular force. In order to decide if that's going to be a hydrogen bond or not, what you do is you look at the hydrogen within the intermolecular force, and it should be directly covalently linked to an N, O, or F. Otherwise, it's not a hydrogen bond. So there's a force of attraction between this hydrogen right here and this oxygen right here. Okay, so let's determine the intermolecular force. So for NCl, if I look at this, I'm going to draw the Lewis structure. We always start with that Lewis structure. So remember, we're looking for those lone pairs on that central atom. We want to know what the shape is. So right here, we have one lone pair. We have 3 atoms bonding to it. That is going to be an asymmetrical shape. It is going to be trigonal pyramidal, which we know is going to be a polar molecule. All right, so if we have something that's polar, okay, first of all, everything is capable of London dispersion forces, everything, okay? So there are electrons that can move, okay, but it's also polar, which means it has a permanent dipole, so it is also capable of dipole-dipole. Okay, the main intermolecular force will be the strongest one, which is dipole-dipole. Okay, so CH4, start with that Lewis structure. Everything bonding to the carbon is the same. It is a tetrahedral shape, which is going to be symmetrical, which means it is nonpolar, which means the only intermolecular force it's capable of is London dispersion forces. So the way a methane, or CH4, attracts another methane is if the electrons happen to move in one spot to create that negative end and positive end so they can attract each other. All right, so HF, for this one, it's 2 atoms, so they are different. So it is going to be a polar molecule / polar bond. Okay, so it's polar, which means that, well, first of all, everything is capable of LDF. There are electrons, they can move, they can create more temporary dipoles. It is polar, so it's also capable of dipole-dipole. And we know it's a hydrogen covalently linked to a fluorine, so that would also be considered hydrogen bonding. And so its main intermolecular force will be the strongest one, which is hydrogen bonding. Okay, so what does this ultimately mean? So what this ultimately means is that it impacts the physical properties. So the stronger the intermolecular force, the harder it is to separate those molecules, okay? So that means it takes more energy to pull them apart. So the boiling point and the melting point are going to be higher. It's going to take more energy to separate those molecules from each other. The freezing point and condensation point will also be higher, okay, because they have a tendency to want to come together and bond or interact more because they're more attracted to each other. And also, they will mix if they have similar IMFs. So polar will mix with polar, nonpolar will mix with nonpolar, and of course, if you've got hydrogen bonding with something that also hydrogen bonds, then that's also going to be much more miscible, or they will mix more readily. All right, so we're going to compare the boiling points of these. So first thing, we have to determine what the IMF is. So I have hydrogen bonding directly to a fluorine, okay? So technically, remember, everything is capable of LDF, okay? It is polar, so it's also going to be dipole-dipole. And it's a hydrogen directly covalently linked to a hydrogen, so it's also got H bonding. All right, so CH4, anytime you guys see a hydrocarbon, carbon and hydrogen in the molecule, it's automatically going to be nonpolar, which means the only thing it's capable of is LDF. Same thing for this one. It's nonpolar, it's carbon, it's hydrogen, so it's only going to be capable of LDF. All right, so we already know what the shape of this one looks like because we did this earlier. It's trigonal pyramidal, which is asymmetrical, which means it is polar. Everything is capable of LDF though. It's polar, so it's also capable of dipole-dipole. All right, so if we're gonna rank the boiling points, okay, remember the strongest one is gonna be your main intermolecular force. So HF should have the highest boiling point. The next one, well, we've got a permanent dipole, so that would be NCl. Okay, now we've got two with the same exact intermolecular force, so now we're going to compare the size. Okay, so the one that's got a higher size would be C2H6, but it's not because of the size, it's because it's got more polarizable electrons. And then the last one would be the CH4. All right. So remember, if you're comparing the same intermolecular force, then you go and you look at the size. Okay, the one with a bigger size or higher surface area just means it has more polarizable electrons, more chances to make these temporary dipoles. All right, so there are a few other types of intermolecular forces. Okay, so there's something called dipole-induced dipole. Okay, so this would be a force of attraction between a polar molecule and a nonpolar molecule. So it has to be two different substances interacting with each other. So if I have water, which we know is highly polar, and it mixes with something that is nonpolar, so that would be CH4. So you have to have a nonpolar molecule interacting with a polar one. So if we were to get a little bit of CH4 to mix into the water, the reason that that could happen up to a very small extent is because it's dipole-induced dipole. So what ends up happening is we've got something with a dipole, so negative and positive end. That means that it can move or influence the electrons in a different molecule. So it pushes them to one region, and then that's what forms that attraction. Okay, it induces a dipole. Then we also have ion with dipoles. Okay, so if you have ionic compounds, they're typically soluble in water. That's because the ions have a full charge. That full charge attracts very, very strongly to something with a dipole or a polar molecule. So this is actually much stronger than hydrogen bonding, okay? So anytime that you have an ionic compound and it's dissolving into water, that's because the ions are attracted to that polar molecule, okay? And then you have something called ion-induced dipole. This is where you have an ion and it's interacting with a nonpolar molecule. So this would be like if I had a sodium ion, or I try to dissolve a salt, some ionic compound, into something that's nonpolar. Probably not that, but anyway. So there are these other intermolecular forces. We're going to primarily focus on hydrogen bonding, dipole-dipole, and LDF, but just note these other things do exist, okay? So it's when I have all three of these, it's something interacting with something different though, okay? All right, so just keep in mind whenever we're talking about these intermolecular forces, every single intermolecular force is a force of attraction. It's just how does that force of attraction happen? With LDF, it makes temporary dipoles, okay? So the temporary dipoles attract temporary dipoles. And a dipole-dipole, so a polar molecule, you have a polar molecule attracting another polar molecule. And then with hydrogen bonding, again, it's a polar molecule attracting another one. It's just a very, very strong intermolecular force. And also, on a side note, for IB actually does not define hydrogen bonding as a van der Waals force because it's so much stronger than the other two. Okay. All right.